Everything that you think you know about the Big Bang is wrong, and I am certainly not talking about some conspiracy theory here. I am talking about what actual physicists believe versus what they taught us in school. Because here is the thing that is going to blow your mind. The vast majority of physicists today don't believe the Big Bang was the beginning of the universe. Please let that sink in for a second. The Big Bang wasn't the beginning. So, what was it? What actually banged? Was it a singularity? Was it nothing? Something else entirely? Stay with me, because by the end of this, you are going to understand something that even most science teachers get completely wrong. If you are captivated by the mystery of how the universe truly began and want to see more mind-bending cosmic stories, smash that like button and let the universe know you are watching. Every click helps keep the search for the unknown alive. Now, before we dive into what the Big Bang really is, we need to go back, way back. Because humans have always looked up at the stars and wondered where all of this came from. The ancient Greeks thought the universe was infinite. The Hindus believed it went through endless cycles of creation and destruction. And then in 1687, a 44-year-old named Isaac Newton changed everything. He published his famous Principia and showed that the same laws of motion here on Earth apply everywhere in the universe. Gravity was born. But here's where it gets interesting. Newton had a massive problem. If gravity pulls everything together, why doesn't the entire universe just collapse in on itself? The universe must be infinite with no center, everything perfectly balanced. The static universe was born, a universe that never changes, never grows, never shrinks, just sits there forever. And for over 200 years, everyone believed this. But there was a crack in the foundation, a problem so obvious that once you hear it, you will wonder how anyone missed it. When you look up at night, you see stars and you see darkness, right? But if the universe is truly infinite and eternal, like Newton said, you should be able to look in any direction and see a star or a galaxy. The entire night sky should be as bright as the sun. And yet, it is not. Something was very wrong with this picture. Enter Albert Einstein. In 1915, Einstein drops his theory of relativity and turns physics upside down. He discovers that as you speed up, time slows down. Space and time aren't separate things. They are woven together into one fabric, space-time. And gravity, it is not a force pulling things together. It is the bending of space-time itself. The sun doesn't pull the Earth. It warps the fabric of space, and the Earth rolls around this curved surface like a marble on a stretch sheet. Now, here is where it gets wild, and I need you to pay close attention, because this is going to connect to something massive later on. In 1919, during a total solar eclipse, scientists tested Einstein's theory. If he was right, light itself should bend around the sun. And guess what? The stars shifted during the eclipse exactly as Einstein predicted. He became an instant celebrity. The Times of London declared Newtonian ideas overthrown. But Einstein immediately ran into the same problem Newton faced. His equation showed the universe was unstable. It had to either expand or collapse. And Einstein, he hated that idea. So he did something interesting. He added a cosmological constant to his equations. Basically, he said empty space itself has energy. He could then tweak this value to keep the universe static and unchanging. He would later call this his biggest mistake. But hold that thought, because we are going to come back to this, and you are going to see why Einstein might have actually been right all along. While Einstein was wrestling with his equations, astronomers were discovering something that would shatter everything we thought we knew. For centuries, people had seen these fuzzy clouds in the sky. They called them nebulae. The most famous one was Andromeda. Nobody knew what they were. Were they just clouds of gas in our galaxy, or were they something more? A brilliant woman named Henrietta Swan. Leavitt figured out how to measure the distance to these objects. And when Edwin Hubble used her method to measure the distance to Andromeda, his result changed everything. 900,000 light-years away, far beyond our galaxy. In that single moment, the universe we knew increased in size by 1,000,000 times. Those fuzzy clouds, they were entire galaxies, islands of stars, just like our Milky Way. The universe was suddenly unimaginably bigger than anyone had dreamed. But Hubble wasn't done. He noticed something even more shocking. Most of these galaxies were moving away from us, not just drifting, racing away at hundreds of kilometers per second. And here is the kicker. The farther away they were, the faster they were moving. Exactly what you would see if the universe itself was expanding. The static universe was dead. Einstein's equations had been right. The universe was dynamic, changing, growing. Now, think about this for a second. If the universe is expanding right now, what happens if we rewind the clock? Everything gets closer together, denser, hotter. Keep rewinding, and you get to a point where everything in the universe, all the matter, all the energy, all of space itself, is compressed into an extremely dense state. A Catholic priest named George Lemaitre called it the primeval atom. He said we are living in the smoke and ashes of a very rapid fireworks display. And because space and time are linked, this wasn't just the beginning of space. So it was the beginning of time itself, a day without yesterday. This is probably what you learned in school. The Big Bang started from a singularity, an infinitely dense point where all the laws of physics break down. Stephen Hawking and Roger Penrose even proved mathematically that this singularity must have existed. Case closed, right? But here's what they don't tell you in school. This is almost certainly not true. And we are going to get to why in just a moment. But first we need to understand what happened after this beginning. You know, physicists figured out that right after the Big Bang, the universe was so hot that it was basically one giant nuclear reactor. Protons and neutrons were snapping together, forming the nuclei of hydrogen and helium atoms. They predicted that 75% would be hydrogen and 25% would be helium. And when astronomers measured it, they were exactly right. But they didn't stop there. They realized that about 380,000 years after the Big Bang, something incredible happened. The universe had cooled down enough that electrons could finally attach to atomic nuclei. And in that moment, all the light that had been trapped in this hot soup was suddenly free. It flew out through empty space and has been traveling ever since. If we could find this light today, we would literally be looking at a picture of the Big Bang itself. The hunt was on. By the 1960s, scientists at Bell Labs were testing a radio antenna when they detected a strange hiss in their data. They tried everything to get rid of it. They even cleaned pigeon droppings out of the antenna. Nothing worked. And then they realized what they were looking at. It was the cosmic microwave background radiation, the afterglow of the Big Bang. Light from 13.8 billion years ago, stretched and cooled by the expansion of the universe. They won the Nobel Prize. The Big Bang had its crown jewel. But here is where things start to fall apart, because there were three massive problems with this story. Three things that made no sense at all. And this is where we are going to discover what really happened, okay? The first problem is called the horizon problem. When scientists mapped this cosmic background radiation, they found something shocking. The temperature is almost perfectly uniform across the entire sky. 2.7 degrees Kelvin everywhere you look. But here's the thing, there wasn't enough time for the temperature to even out. Even traveling at the speed of light, opposite sides of the universe couldn't have communicated with each other in just 380,000 years. It would have taken trillions of years. So, how is the temperature so perfectly uniform? The second problem is the flatness problem. Space can be curved in different ways. It can be flat, where parallel lines stay parallel forever. It can curve inward where parallel lines converge. Or it can curve outward where parallel lines diverge. When we measure the curvature of our universe, it is almost perfectly flat. But here is what makes this insane. A flat, expanding universe is incredibly unstable. It is like balancing a pencil on its tip. The slightest deviation and it should rapidly diverge, either tearing the universe apart or causing a collapse. So, why is our universe so perfectly flat? The third problem is the monopole. At the high energies present in the early universe, particle physics predicts that huge numbers of these exotic particles called magnetic monopoles should have formed. These are hypothetical magnets with only one pole either north or south with no opposite. The problem is, we have never found a single one. And if they existed, they would be so heavy they would have prevented the universe from expanding at all. And beyond all of these problems, there was still the singularity itself. Most physicists felt something was off. Einstein called the idea that the universe started at a singularity repugnant. The mathematics seemed to be pointing to something that couldn't actually be real. This is where a brilliant physicist named Alan Guth comes in. And what he discovered is going to completely change everything you think you know about the Big Bang. Guth was thinking about phase transitions. You know, like when ice melts into water or water boils into steam. But there are strange phase transitions too. Pure water can be cooled below freezing without turning to ice. It is called supercooling. The phase transition gets delayed. Guth started thinking, what if the early universe went through a similar delayed phase transition? And then he calculated something that made him realize he was on to something huge. If empty space has energy, which quantum mechanics tells us it does, and if this energy drives the expansion of the universe, the rate of growth would be absolutely insane. In less than a trillionth of a second, the universe would expand by at least 100 trillion times. And he called this period inflation. And here is the magic. This period of rapid inflation immediately solved all three problems. The flatness problem solved, because no matter what shape the universe started in, this rapid expansion would flatten it out perfectly. Like inflating a balloon, the surface gets flatter and flatter as it grows. The horizon problem solved because regions that seemed too far apart to have communicated were actually very close together before inflation. They had plenty of time to reach the same temperature. The monopole solved. The monopoles simply don't get created during the supercooled phase. But inflation did something even more incredible. Remember those tiny variations in temperature we see in the cosmic microwave background? Those slightly hotter and cooler spots. Inflation explains where those came from. Quantum fluctuations in the inflation field get frozen into the fabric of space as it expands. And these tiny variations, they are the seeds of everything. Gravity pulls matter toward the denser regions. And over billions of years, these tiny ripples grow into galaxies, stars, planets, and us. If it were not for these quantum fluctuations during inflation, there would be no structure in the universe at all. No galaxies, no stars, no you, no me. So now we can finally answer the question, what actually banged during the Big Bang? We start with empty space. No matter, no light, nothing. But this empty space is filled with an underlying quantum field, the inflation field. This field causes space. Something the size of a grain of rice grows bigger than our entire observable universe in less than a trillionth of a second. And here is the key. At this point, there is still nothing, just rapidly expanding empty space. And then inflation ends. And bang, all of the energy in this inflation field instantly converts into matter and radiation. This is the hot, dense Big Bang you learned about in school. The cosmic microwave background, the nuclear reactor that formed hydrogen and helium, all of it comes from the vacuum energy of empty space in that moment. No singularity needed. Big Bang wasn't the beginning. It was the moment when inflation ended and all the vacuum energy became everything we see today. But here is the part that is going to really blow your mind. Inflation doesn't end everywhere at once. It happens in patches. So, while inflation might decay into matter and radiation here, creating our universe and our Big Bang continues inflating outside our universe, spawning potentially infinite numbers of other Big Bang universes, each one with its own physics, its own constants, its own story. The multiverse is born, and we just happen to be inside one of these bubbles, okay? This is the most widely accepted view among physicists today, not what you were taught in school, right? When I learned this just 2 years ago, they told us inflation happened after the Big Bang. The singularity was still presented as fact. No mention of the multiverse, but science evolves. New evidence comes in, better theories emerge, and the inflationary Big Bang is currently our best description of how everything began. Okay, now, does this mean we have all the answers? Absolutely not. But some physicists argue that inflation is too flexible, not falsifiable enough. The multiverse makes many scientists uncomfortable because we might never be able to test it directly. But here is what we know for certain. The hot, dense Big Bang definitely happened. Everything in the universe used to be incredibly close together and much hotter than it is today. We can literally see the evidence in the cosmic microwave background. That is not up for debate. What caused that hot, dense state? What came before inflation? Those are the questions still being explored. Alan Guth himself said, "The Big Bang theory was never actually a theory of the bang. It says nothing about what banged, why it banged, or what happened before it banged, and that is where we are today." Standing at the edge of the unknown, looking back at the moment our universe was born, understanding more than we ever have, but still chasing the deeper mysteries of what started it all. So, the next time someone tells you the Big Bang was the beginning of everything, you will know better. You will know that the bang wasn't the beginning. It was a transformation, a moment when empty space filled with vacuum energy became everything we see, touch, and are made of. And that is somehow even more mind-bending than any singularity ever could be. Hey, don't stop here. The universe is full of secrets waiting to be uncovered. Click on the next video and join us as we explore even more astonishing mysteries about the cosmos, from black holes to the edge of reality itself.